Hello everybody. Today we come to the last lesson in this chapter. Up to now we have been looking, or mostly, at problems where the force given in our formula was constant. And today we will look what happens if this force is changing. For instance, we have already done an example for that if you go back and look at the chapter with springs. So the chapter is 6.9, work done by a variable force. Let's, as a repetition, have a look at this example. We have a force given. I just draw the plot here. Force as a function of displacement. And for instance, we can say there is a 7 Newton force acting over a distance of 5 meters. What is the work done? Well, the work done then is force, which is 7 newtons, times displacement 5 meters. We assume that force and displacement are in the same line, so beta is 0. So this amounts to 35 joules. We can have a look at this number of 35 to be 7 times 5. So basically the 7 is this side over here and the 5 is this side below here. So it's a rectangle and this 35 Newton correspond, so to say, to the area of this rectangle. As a repetition, let's have a look how it was done with springs. So using a spring, the force was increasing the longer the spring gets. So we had at the very beginning the spring is not stretched, so at the beginning it is very easy to pull, and the more we stretch this spring the harder it gets. And the diagram was given Hooke's law that this is proportional. So for instance, we can say we have the final given force of 12 Newton, which is at 0.5 meters, and at the beginning the force was 0. So here we have had the idea that we said instead of the maximum force we take the average force. So this bar just tells us that it is the average force. And the average force in our case was the beginning, which is 0, the end, which is 12 newtons, divided by 2, times 0.5 meter, which is, first term is 6, so we get 6 times 0.5, 3 joules as the work done here. So what is this average force? It's 6 Newton. And we could draw it here. So in reality, I have a force that is increasing from 0 to 12, and I replace it by a constant force of 6 Newton. So 6 times 0.5 is 3. So again here, just as we did above, if we compare, we can say the area corresponds to the work done. However, this green area actually is not the area that we want to calculate or what we are supposed to do. In reality, what we are supposed to calculate is this area with the true changing force. But of course, if you cut away here this tip of the triangle, you can just put it in here and you can see that the area of the triangle of the big one is the same as the area of the green one. And this basically is the idea. We can just say the area here corresponds to the work done. So let's look at the general arbitrary function. F as a function of S, and it could look something like that maybe. And if you want to have the work, we could just make some slices here. And then say, okay, we draw rectangles. And then each rectangle has the height of the force. So this is a certain force given. And this is a certain displacement, delta S, given. And each of these rectangle is a small work which is done. And if you want to calculate the total work done, we can just say, well, it's the work done here, plus that, and so on. So we can say that the total work is given as the work in the first part and in the second, in the third, so on, up to the last one, which we write Wn. All these works are then F times S, F1 times delta S1, so it's this area, plus F2 times delta S2, which is that one, plus F3 times delta S3, which is the green one, and so on until we have all of these rectangles added. Or in a little bit more mathematical way, we could say the total work is the sum. So I use here this capital sigma, and it is F with the index I times delta S with the index I, and I is running from 1 to the last one. So this is just a fancy writing to do that. The result will get better and better the thinner we do these slices here. So delta S has to become smaller and smaller. And if these slices are infinitely small, we are back to what we had. We are back to the area. The smaller the slices, the more precise the result. So the idea then is the work done is equal to the area under the curve in the force as a function of S diagram. So if you want to draw that again, we have the F and the S, and then we have some graph given, and then the work done is all these infinitely small slices added up, which is then just the area. So the area corresponds to the work done. Later in maths, you will learn in a mathematical way how to solve that. And this is then called the integral, and you will write the formula for the work that the work done is the integral of f times ds. ds is the thickness of such a slice, and this is the force, and this symbol here for the integral is just some sort of abbreviation of the sigma sign. And then you say it has to go from a to b. So we started here and ended up at this point here. So I'll not put this as a formula. This is more just a promise for the future. Let's do an example. So let's assume that our force is very small at the beginning and gets larger and larger, but it's not regularly like in a spring, but it's doing it in such a manner. So towards the end, it gets tremendously larger. So the final force here is 100 Newton. And the final displacement 5 meters. So what we have to calculate is this area given here under the curve. So how is it done? Of course, we have to know what this function is. And let's assume this is a circle, or so to say an ellipse, which is going around here. And therefore we can say that this part here is 1/4 of an ellipse, which is given here. And the yellow area therefore is the rectangle minus this blue area which corresponds to what we are looking for. So the rectangle simply is 100 Newton times 5 meters. And we have to subtract 1/4 of an ellipse. So the area of an ellipse is A times B times pi. So the height times the width, or the long times the small axis, half axis, times pi. So it's 1/4 of it, so it's 1/4 times 100 Newton times 5 meters times pi. And we get 100 times 5, 500 joules for the box. And 1/4 times 100 times 5 times pi is 393 joules, which amounts to 107 joules for the work done.